Institute of Theoretical Physics of the State University of São Paulo. I want to welcome you all for this school on QCD Meets Gravity. And just as curiosity, how many of you have been here before? Amazing. And how many of you is the first time? So really great. It's great that you're coming and really welcome. And I'm sure you're going to have a very productive week learning about the connections between spin 1 and spin 2 gauge fields. So without further ado, I'll pass the word to Riccardo Sturani, who, you're going to introduce Riccardo.
Right, yeah. All right, so good morning, everyone. It's a pleasure to welcome you all to this school. My name is Thales Azevedo. I am one of the organizers of the school. I'll be here for this week and the next week as well, for those of you who are going to be here. And it's my pleasure to introduce Riccardo Sturani. He's a professor here at the ICTP. And I guess he's also going to introduce himself, but he's going to give the first lecture today, and he's going to tell you about everything you wanted to know about gravitational waves and were afraid to ask, right? So please fill him with questions.
Okay, very good. Thank you. Okay, this is low in battery, but I have this other one. See? Okay, very good. So how many are you? 1, 2, 3. Okay, you know everything. So I will be giving a short mini course only today and tomorrow. Then you will have 3 other lecturers. One of them is here, Henrik. He's probably jet lag, but well awake. And so just a little poll. So you are some. How many of you come from, let's say, outside Latin America? Oh, that's a lot outside Latin America. So can I go quickly among the non-Latin America? Where are you from? I mean, not your passport, but whether you're doing your master, PhD, or whatever. Queen Mary, yeah. Check, right, yeah. London, Queen Mary, okay. So I'm just doing the poll of the non-Latin American participants. Edinburgh, okay. So Imperial, okay. Oh, UK wins, UK. Sweden, yes, good. In France, good. So we have, I think that's a good percentage of Europeans. So let's make a quick poll of Latin America. Let's say how many from Mexico? Oh, good. Oh, okay, we usually don't have many people from Mexico, good. So say Venezuela, I guess nobody. Colombia, Venezuela, say? Okay, Colombia, yes. Colombia has a strong tradition in amplitudes. So let's say Peru, Chile, Bolivia. Okay, not many. Argentina? Okay. Warming up for the World Cup. We are having an event also in June during the World Cup. Be prepared. And so, okay, but then did I miss any country which is not Brazil in Latin America? Yeah. Uruguay, sorry, Uruguay, yes, sorry. Of course, no. Never meant that, never meant. Did I miss any other country in Latin America which is not Brazil? Yes. Colombia, you arrived late, I was asking earlier. Okay, good. So Brazil, how many say northeast in Brazil? Oh, nobody, yeah. Oh, too few, not northeast. And then, I mean, including Bahia. Bahia is northeast. Okay. So, and then okay, Centro-Oeste, Center-West. Yeah, where? Goiás, very good. And then, let's say, Southeast, Rio, São Paulo. I guess most of people. And then the real south, from Curitiba down. Okay, it's okay. And then another poll I need to make. So I guess most of you are either astro or particle, broadly speaking, particle. So who is astro here? Yeah, you're not really astro, come on. Who is more particle oriented? Okay, basically most. So who is neither particle nor astro? So what are you doing then? No, particle, I mean field theory in general. I mean, not I didn't mean particle phenomenology, field theory in general.
Where do you fit GRQC? Is that after particle?
GRQC, well, okay, GRQC with different approaches than field theory. What can be different than field theory?
Classical general relativity.
It's a field theory too. Come on. Sorry, when I meant particle, I meant. Okay, very good. So since very few of you are, yes. It's not on. Thank you. So since very few of you are in the astro business, I will introduce you. I will try to. I will do my best to introduce to the. Actually, to have the tools to read papers, no, to read the news about gravitational wave detection and so on. You might already have, but let's do this review together. And then, of course, we go into more details of the mathematical details of what, going in depth in the theory of gravity, I mean, with other lecturers, and see what can we learn about the dynamics of systems which are gravitationally, whose dynamics is ruled by gravity. Okay, so as you know, so we are here because there was a detection of gravitational wave. I mean, the first detection was 10 years ago, no, in September 15. Then it was announced in February 16, and it changed many scientists' life. Like, you know, people working in the field didn't have a job, soon could get a job. And no reference to any specific person. And what is the detector? The detector is an interferometer. I will not go into the detail. An interferometer is a ruler, is a very precise ruler. But it's a ruler that doesn't just measure the distance from one point to another, but it measures the differential distance between this mirror and the beam splitter and this mirror and the beam splitter. So the idea is there is a laser is split into orthogonal arms, then it goes back. And the intensity of the recombined light is proportional to the the difference in phase. Okay, so I have some notes that are not yet in the website, but they will be very soon. And in these notes, you find all the details. I don't want to go through the details now because then it would be really another kind of mini course. But let me tell you a little bit about the phenomenology. So what happens here is the gravitational wave is coming from a very distant source, like a binary system of black holes. So these objects are very compact. They are kilometer scale, tens of kilometers, hundreds of kilometer scale, okay? So these objects are basically human scale, whereas this distance is not human scale. It's really astro scale. It's of the order 10 to the 2, 10 to the 3 megaparsec. Since you're not astro people, so how many of you don't know what is a megaparsec? I will tell you in a second. Okay, so most of you know, but then, so this is really an astro scale, and this is way out of our galaxy. So of course, this design is, this is supposed to be the Earth, and that's, so this drawing is way out of scale, of course. So the Earth is 1,000 kilometers. Our galaxy, the Milky Way, is of the order of 100 of kiloparsec, few hundred of kiloparsec, and then we go to megaparsec to see the objects in faraway galaxies. Then you might think, okay, but why don't we see, if we are able to see so distant objects, why don't we see nearby objects? Why don't we see objects in our galaxies? After all, not you because you were too young. You were not even born, but 40 years ago there was a supernova in our galaxy. We see catastrophic events in our galaxy. We'll come to that. So, but the first thing to understand is that when you recombine the signal, basically you need to have some effect, some differential effect in the two mirrors. So, without knowing anything, so this is the size of the mirror. You must have seen some pictures, some real picture of this interferometer. They measure kilometers. So what do you expect would be the typical frequency? Any detector cannot detect any frequency, okay? Our mobile phone detects some specific frequency, whatever. What will be the typical frequency that will be detected by the interferometer? If you do the computation that is in the notes, basically you will see that the answer, the intensity of the recombined light, how it depends on the differential motion of the two arms will depend with something like, well, this L. After all, I mean, we don't have many scale in the system, no? I just told you there is a gravitational wave that arrives with some frequency. Of course, the distance shouldn't affect. The distance just decreases the amplitude. And this is the effect. So this is the intensity of the recombined light in the interferometer is proportional to this. So you would expect that the maximum sensitivity, of course, when L goes to 0, you have 0 sensitivity, which is expected. And then the maximum sensitivity is then when this is pi over 2. Okay? And so if we think, I mean, what is the typical frequency that LIGO, Virgo, Kagra are working at? You know what is that? It's also, you know, there is always the analogy of the acoustic, no? Virgo and LIGO and Kagra are listening, because it's sort of acoustic frequency. Okay? So omega is 2 pi the frequency, and the typical frequency is 100 hertz. So if you do the math, 1/4, and then you get a length which is in second. Of course, lengths are not in second. We are missing the speed of light. Or kilometer per second. I will never use the speed of light until I want to get real numbers. Of course, when you do theory computation, we set the speed of light equal to 1, and also g most of the time, g Newton to 1. But at the end of the day, if you want to compare to physical objects, like an interferometer, which is on the Earth somewhere, you have to state back the standard units. So we do the math. Here is a 3/4. It's 0.75. And this is 10 to the 3 kilometer. And so this is 750 kilometer. So they told you, I mean, I guess you must have heard, no, that LIGO Virgo are sensitive to 100 hertz-ish. And so the typical length of the interferometer that responds maximally to this frequency is 750 kilometers. But LIGO Virgo are not 750 kilometers as physical size, you know. I mean, there's no place where you can build an interferometer of this size. The fact is that here there are some cavities that recycle the photon. So 750 kilometers, I mean, again, this is order of magnitude, is broadly the optical path of the photon. So the photon goes back and forth several times in the arms. And so basically you can enhance its path through these cavities without having to build an effective interferometer of 700 kilometers. Then you might say, okay, but then if we can build an interferometer only of 4 kilometers, let's put here 4 kilometers and let's look at the frequency which are corresponding. Well, that was my first objection, and that shows why I'm not an experimentalist. Because at the end of the day, you have to compare to all sorts of noises that you might have. Okay, and all sorts of noises, they basically, for whatever built on Earth, you cannot go below a few hertz. You cannot go below 10 hertz. I mean, if you think of the Hertz, is related to the scale of the second, right? The Hertz is the inverse of the second. And so whatever is human is associated to the Hertz. I mean, our art, for once, and all vibration due to human activities and vibrations, seismic vibration and so on, they blows up below 10 hertz. So if you want to see something with a device on Earth, you better go above 10 hertz, so with the length sufficiently small. But then you cannot go too high in frequency, and usually the frequency, the ballpark of any Earth base, let's say 10 hertz, stops at the kilohertz, because at the end of the day, if you increase too much the frequency, then you want to sample the signal at a very short time, okay? If you go to a very high frequency, it means that you are collecting the photon that measure the position of the mirror on very short time. And on very short time, you start seeing the granularity of light. You start seeing short noise. And then you might say, okay, let's increase the power of the laser. The problem is that if you increase the power of the laser, you start hitting the mirror start bending, and so on. And so basically, there is some fundamental in the sense of the experiment, limits to anything you can do on Earth in these frequencies. And so you say, okay, fine. We are bound to look at things in this frequency. So we put this frequency here, and so we get the optimal size of the interferometer. The optimal size of the interferometer is way too big, so there are the cavities that can do the game. So if we if the photons go back and forth a few hundred times, it's fine. We have the right length for being for detecting in this frequency. By the way, is this frequency okay to detect binary black holes? Well, what is the frequency that is emitted here? Let's forget the gravitational, the cosmological redshift. How do we compute the frequency? From the Kepler's law, no? If you have a bound system, the typical velocity is gm over r. Of course, let's forget eccentricity, no? Circular orbit, and this is simple, okay? So, and this is m, the mass, the total mass of the system, just Kepler's law, Newtonian Kepler's law. This is the last time I will write g, okay? So g for me is a converter of mass into length. So v is dimensionless, because I don't want to write the speed of light. And so this has to be dimensionless too. And so that means that g is just a converter of mass to length. So whenever you see mass, you should think about length. So since most of you comes from field theory applied to particle and so on, you have to do a step. You're used to associate mass to inverse length, forget it, okay? We never do that. So why you usually associate mass to inverse length? Because you are understanding there is an h-bar here, okay? If there is an h-bar, then you're right. But we never do h-bar because these systems are way classical. Huh? We are talking about solar mass object. There's no quantum effect here. Even at the horizon, the curvature of the horizon is nothing to do with the Planck scale. It's to do with the kilometer in the square. Okay, kilometer in the square, you cannot think of anything farther away from the Planck scale. Okay, so h-bar will never enter here. Tomorrow maybe I will talk 5 minutes about h-bar to tell you why it's irrelevant. So for us, g is the converter of mass into length. Don't forget. Okay, fine. So actually we'll be using the Kepler's law in a slightly disguised way. So we'll use this as v cube equal to pi gm omega orbital. Okay, I multiply by v over r is omega, okay? I mean, these two are completely equivalent, no? I multiply by v both sides, v over r I substitute by omega orbital. And so this is the way I will use the Kepler's law all throughout. So the velocity of the system cube is linear in the orbital frequency. Okay, what else do we want to do? Okay, about the astro. So megaparsec, everybody knows what is the megaparsec, but since I prepared it, let me explain to you anyway. So, megaparsec is the first example of the contamination of astro jargon into gravity jargon. You know? So gravity as a field theory, of course, has been studying heavily, with the tools of particle physics. But of course, it's describing events that are happening in the astronomy arena. And so we have to, at the end, we want to make prediction and talk to the astronomers that do the observation. And so we have to understand how to translate in the standard units that are used there. By the way, I haven't finished here. So if you want this object, the Kepler's law, what is the typical frequency? We want the frequency to be around the hertz and the kilohertz. And so the velocity can be anything between 0 and 1. So basically we want m omega to be smaller than 1. And that tells you that basically you just have to tell me what is the mass in seconds, okay? The solar mass is 1.5 kilometer, which is equal to 10 to the 33 grams. Okay, this is just effect. I mean, that the mass of the sun is this, it's effect. And then my setting G21 allows me to write this equation. This shouldn't shock you, no? The mass of the sun can be measured in kilometer, in grams, or in seconds. Now I don't remember the exact value in seconds, but it is of the order of 10 to the minus 6 seconds. You divide this by the speed of light. I think it's, okay. Let's do it. 1.5 kilometer divided by 3, 10 to the 5 kilometer per second. So kilometer and kilometer simplify. Seconds, so this is 2 times 1.5. So this is 0.5 10 to the minus 5. So yes, it's 5, 10 to the minus 6 seconds, okay? So the solar mass is of the order of microseconds, of the order of the kilometer, or of the order of 10 to the 33 grams, but we'll never need this, actually, the expression of the solar mass in grams. By the way, as a fun fact, I will write here because it's somehow decoupled. But as a fun fact, the solar mass is m Planck cube divided by m proton square, roughly. I mean, within factor of few. Why is that? Well, it's not part of this course. You study if you want. But it's a fact. And there is a reason for that, but I will not tell you. Even students, I mean, I do it when I teach GR, I do this, and I realize that after a few weeks after the exam, my student has forgotten it. So I lost hope. So if you're interested, you look it up yourself. Okay, so this is the ballpark. And then if you plug it here, you will see that for having omega of the order of 100 hertz-ish, of course, there are the 2 pi's, that it's a factor of 6 is not completely negligible. So you see, the mass times 2 pi divided, say, the kilohertz. So let's put this m divided by m sun by m sun. This has to be smaller than 1. And so we have that m divided by m sun must be smaller than 1 kilohertz. 1 over m sun is 10 to the 1 kilohertz. Let's write to the 10 to the 3 hertz. This is 10 to the minus 5 hertz to the minus 1. This is 1 over m sun in second, which is s to the minus 1. And then there are the 2 pi's. No, there is something wrong here. So what I wanted to get, m over the sun should be less than 10 to the, there is something wrong here, sorry. M over the sun, this is, the kilohertz, of course, has to be above. 2 pi kilohertz. Okay, this is m over m sun, must be smaller than. Must be smaller than 2 pi 10 to the 3 hertz, which is second. And then the m sun goes down, it's 5 10 to the minus 5 second and second simplify. So m over m sun must be smaller than order of the order 10 to the 2, 10 to the 3, 10 to the 2. Okay. So this tells you that if the frequency, if the mass is too high, the object is too big. It takes a long time to go around its companion, and so we fall off the sensitivity. But if the mass is small, there's no problem. No? If the mass is small, so if you write, so the amplitude of the signal in hertz. So basically, there will be a cutoff in the amplitude of the signal that is given by the inverse of the mass. Basically, if the mass is large, you stop the signal at a smaller frequency. And so there is a sort of natural cutoff for this kind of experiment at the inverse of 100 solar masses. So the signal, however it is made here, it should stop here. But of course, if you go to lower masses, the signal could go to higher frequency. Okay? Basically, to have the signal inside the band above 10 Hz, you must have the masses not too high. The masses should be solar masses, 10 solar masses, 30 solar masses, and so on. But then you might say, okay, what's the problem in having a smaller mass? A smaller mass will cut off at a higher frequency, but the signal during the inspirer, when V is smaller than 1, will sweep in our band. Well, the problem is that the object has to make a revolution. So if the object is small, what will be its typical size? Can we use this formula again when the object is small? Let's say an object of 1/10 the solar mass will have a size of 100 meters. Well, it depends. No? For instance, the Earth. The Earth is 1,000th of the Sun, but its size is much bigger than this. No, it's 1,000 kilometers. So what happens when you reduce the mass? The object is not compact. The object grows fat just because there's not enough gravitational pull to make it compact. So that's why. So our experiment obliges us to see some sort of masses, because some sort of masses are converted into some sort of distances, okay? And the distances are converted to frequency. But if the mass cannot be converted to frequency like I did here, because here I converted the mass only through G, and that only holds for black holes. If the mass is not converted to distances, because like the Earth, it has a mass which is completely unrelated to distance, then it's not compact, and then forget it, okay? So we need to see compact object. No? This is a question that I usually get when I gave my first seminar about gravitation detection. So why we only see black holes? Couldn't we see extended object? Since the gravitational pull is the same if the mass is concentrated in the center or it's distributed over compact object. Yeah, but if the object is not compact, its size is 1,000 kilometers, then it breaks before it gets to the interesting frequency. Okay? So we need compact object. We need them to be not too massive, and then they could be as little mass as possible, but of course, if you let the mass go down, the signal will be lower, just because the mass is the gravitational charge, so the signal will be proportional to the mass and will not emit enough to be seen too far away. Okay? And also there is an astrophysical problem. Do we know compact objects which are below the solar mass? No, well, all the compact objects we know, they are supposed to come from the collapse of stars. And the star, they need at least one solar mass to build. So you need to accumulate one solar mass, a bit more, then we'll go supernova, and then we'll form a compact object, actually more than one solar mass, okay? So it's impossible to build astrophysically by gravitational collapse a compact object which is smaller than one solar mass, okay? So if we happen to see a compact object of a mass smaller than one solar mass, that means it didn't come from astrophysical collapse. This could happen. Some primordial fluctuation and collapse directly to black hole. Those are the primordial black holes. And those are the primordial black holes that will give a signal at high frequency because they are small, and so they can reach high frequency. Well, that can be, but we haven't seen them. Okay. Let me go a little bit into the details of the detection. Okay. So this was about the distances. Okay. I started here and then I forgot. So if this is distance r, this is our sun, and this is the Earth. We know this distance is 1.5 kilometers. And we want to know this distance, the distance from either the sun or us from the distant star, a star well outside our solar system. You know, our solar system alone is 10 billion kilometers. So whatever is outside our solar system, we don't even use kilometers anymore. So the idea is that how can you measure this distance? You can measure through the parallax. If going from winter to summer, you have a parallax of 1 second, then by definition, you see that the distance is 1 parsec. That's the definition of the parsec, and that immediately tells you that this is really a definition that comes from the astro business. No? It's really an operational measure. So if you want to measure the parsec, that is basically will be 1.5 kilometer divided by 1 second expressed in radians. So which is 1 over 3 of a degree, which is pi over 180. Okay? So if you do the math, you will see, so this is 1 parsec. This is this is of the order of 3 × 10⁻16 kilometer. Okay? So this is the typical unit of measure that astrophysicists use for whatever is outside our solar system. So 10 billion kilometers is the size of the solar system, and then forget kilometers. You won't talk anymore about kilometers. You will start talking about parsec, and kiloparsec, and megaparsec. And this is the conversion. So basically, the distance from us to the center of our galaxy is of the order of 8 kiloparsec. The luminous matter in our galaxy stops at 20 kiloparsec from the center. Dark matter is supposed to go up to 100 kiloparsec. And then you have the distance to a neighboring galaxy. Andromeda is 0.7 megaparsec, but the distance, the average distance between galaxies, average, is of the order of 4 megaparsec. Okay, all of this in the local universe. Average, of course, the closest galaxy is closer than the average distance to the galaxy, as it makes sense. And so from this, you already get the typical density of galaxy, at least in the local universe, is 10 to the 2 megaparsec to the minus 3, okay? And this is a good number to remember. This is the density of galaxies in the local universe. And another interesting thing talking about numerology is the following. How do we relate to cosmology, to cosmological scale? All of this is about astrophysics. Now we measure distances, so 100 of kiloparsec to be in our galaxy, order megaparsec to go to Andromeda, our neighbor, few megaparsec, the typical distance. This is the density. So how do we go to cosmology? Well, how do we go to cosmology? We introduce H naught. H naught is equal to, okay, there are some controversy about this value, but at the level we are doing things here, I guess we are not worried with a few kilometers per second. So this is the value of H naught. I mean, give or take a factor of 7 kilometers per second per megaparsec. Again, this is a funny unit. I mean, this is just an inverse length. So why don't we give it just in inverse kilometer or inverse megaparsec? Well, it's related to the way it's measured, no? It's measured as a velocity of recession of nearby galaxies. And we know the velocity of recession is measured through redshift. And we know that a low redshift is linear to the distance. So basically, you multiply this by the distance of the galaxy, and you get its velocity of recession. Of course, from the fundamental point of view, it doesn't make any sense to use this unit, but it's very useful operationally. And then, you know, there is GR that relates this to the average density of the universe. Okay? So I want to relate this is on cosmos scale. I want to relate this to astro scale. So this is the typical density of galaxy, and what is the typical mass of a galaxy? How do I? Let's put it 10 to the 12 solar masses. Okay, our galaxy is a bit lighter than that, but we have some few. Our galaxy is about 310 to the 11, but we have some few satellite galaxies. So let's say that this is the density of galaxies. Basically, in any cube of 4 megaparsec of side, there is a 10 to the 12 masses, 10 to the 12 solar masses here. Then I move 4 megaparsec, and I get some other 10 to the 12. So how this is related to that? Well, we know that the universe was homogeneous, right? The CMB has taught us. So as high redshift, we were here. This is my picture of the universe at high redshift. And now I'm drawing a picture of the universe at small redshift. Of course, galaxies are clustered. No? This is the average picture, but galaxies like to stay together in a clump, then there is void, then they stay together in a clump. I'm not worried about this now. So this is high Z. This is low Z. Are the two pictures consistent? Just doing a back of the envelope computation. Let's put the rho from here. This is equal to 8 pi over 3, let's say 8. I mean, at this level of accuracy, you will forgive me. Rho is 10 to the minus 2 megaparsec to the minus 3 times 10 to the 12 solar masses. But 10 to the 12 solar masses, we trade it for a length. So this is 1.5, 10 to the 12 kilometer. Okay? So I want to check the consistency of this picture, which comes from the standard Freeman equation on GR, with our understanding of the local universe. Okay, now we have to do the math, convert the kilometer to megaparsec. Let me check if I have it right, the conversion from kilometer to megaparsec. Wikipedia can tell me. Parsec to kilometer. megaparsec to kilometer. So yes, 310 to the 16, sorry, 310 to the 13, yeah. 310 to the 16 was for meter, 310 to the 13 kilometer. Okay, so let's do the math here. So on one side, we have 7 kilometer per second divided by megaparsec square. And of course, if you want to match the unit, this is 1 over length square, we need the speed of light. 310 to the 5 kilometer per second. So now this is a real inverse length square. And on the right-hand side, 8 times 1.5 is 12. Okay. So it's 1.2, 10 to the 1. This is 10 to the 13. Minus 2, 10 to the minus 11. And then I have kilometer divided by megaparsec square. And then let me write kilometer times megaparsec. Okay? Let's do the math here. Here I have 70 divided by 3, 10 to the 5. So it will become some 2, 10 to the minus 4. Megaparsec to the minus 2. Sorry, 2 to the minus 4 divided by megaparsec to the square. This is 10 to the minus 5. Yes, 2 to the minus 4. And then on the right-hand side, I want to check if this picture match. I have 10 to the minus 11, 1 over megaparsec square. And then I have to put this kilometer to megaparsec. I have done something wrong, probably. So, sorry. Yes, there was a 10 to the 12 of the. This is. Sorry, there was 10 to the minus 2 from the density, but then I had a 10 to the 13. So 10 to the plus 11, okay? I had 10 to the minus 2 from the density, I have this 10 to the 11, and then I have a kilometer over megaparsec. Kilometer over megaparsec, it's 1 megaparsec is 3 10 to the 16. Okay? So here, there should be a 3. It shouldn't be a 4. How come the 300,000 kilometers per second? Yes. 70 kilometers per second, 70 divided by 3. No, this is 10 to the minus 4. This is 10 to the 11. So, this was a 13 in kilometer. Okay, yes. Now we are getting there. This is 1 megaparsec is 3 10 to the 13 kilometers. This is kilometers. Sorry, it was supposed to be right. It doesn't come right. So that's why I should follow my notes. That's why I should follow my notes. Yes. So I have 8, 10 to the 12, 10 to the minus 2 megaparsec to the cube, and then I have 1.5 kilometer in 10 to the 12. So all of these will give me, well, I've done here the computation. I multiply by the speed of light here instead of there. Yes, 70. So 2 10 to the minus 4. Yes, it should be right. So this is 10 to the minus 2, this is 13, this is minus 11. Sorry. This is 13 to the minus 2 megaparsec cube, and then is kilometer divided by megaparsec. Well, it was supposed to be right. I will, in the notes it's right. 3 10 to the 13 kilometers. So here we get of the order of 10 to the minus 3, 1 over megaparsec square. Here we get 10 to the minus 8, but this is not correct. It should be the same order, sorry. How come? Okay, I will put it right in the notes. So sorry, this is this is embarrassing. This is 8 pi over 3, the density, time 10 to the 12 kilometers. Yes, this is 10 to the 10, 10 to the 11. And this is the conversion for kilometers to megaparsec, which is correct. Wait, maybe I was taking the conversion of parsec to kilometers. There was, you see, there was parsec to kilometers. Yes. There was a conversion of parsec to kilometer. 1 parsec is 3 10 to the 13 kilometers. Here is megaparsec. Okay, that's the point. Fine. So 1 parsec is 3 10 to the 13 kilometers. 1 megaparsec is 3 10 to the 19. And so we are right. Okay, fine. I adjusted. So what I wanted to get, apart this little hiccup, is that the local picture that we have of local densities is consistent with the fact that we started with a homogeneous universe whose critical density is set by h naught. And then if we compare it with local density, like 10 to the minus 2 over megaparsec cube, or 10 to the 12 galaxies, that fits this equation. I mean, if you do the computation right. Okay, because this is 10 to 90, and then this is 10 to minus 90. So it fits the picture that the galaxy we see today in our local universe are sort of the collapse of the clump of matter that was originally evenly spread. Okay? Good. So, and now we come to the question, why we don't see this object nearby? Why we have to look at these distant galaxies? I mean, after all, it would be nicer to see objects nearby because they would be stronger. So this has to do with the intensity of the signal. So the idea is that intensity of the signal will decrease as 1 over r. So if you see things nearby, that should be easier. But at the same time, we need to have the sources around. So how many objects of these we expect in our galaxy? So in our galaxy, do we see binary system? Are binary systems common in our galaxy? I mean, binary systems are very common. I mean, the majority of stars is in binary system, okay? So if, our sun is not, is having a lonely life, but he has his own planets to cheer his life with. But most of the stars are in multiple systems even, okay? Of course, a star is not good for us. A star is not good for us because we need something compact that revolves 100 times per second, 1,000 times per second. No? Something that has to be compact, a star wouldn't do. But a star will eventually end its life and become a compact object. It will go supernova, become a neutron star or a black hole. Will it be okay to remain bound? Maybe yes, maybe not. But even before the detection of gravitational waves, we've seen neutron stars in our galaxy which are in binary system. We know that there are 10 neutron stars in binary system with another compact object. There are many more in binary system with a star, but compact object in binary system we observe 10-ish in our galaxy. And there must be many more because the neutron stars we see are the ones that have their lighthouse beam pointing to us. Okay, and how far away are they from coalescence? They are hundreds of million years. Okay, so since we observe in our galaxy just electromagnetically through the light beam, the radio beam of the neutron star, a neutron star which is in a binary system. How do we know in a binary system? Because if a neutron star is alone, the light beam is emitting steadily. If it's in a binary system, it has some modulation with the orbital system. And so we have 10-ish systems that are in compact system, and they will all merge in 100 million years. So that's the first guess of the number of events that you had to expect per galaxy. And the number of events of coalescences per galaxy is of the order of 1 every 100 million years. Okay? That's just a very, very rough estimate from what we see already in our galaxy, just the binary system we see in our galaxy. That means that if you want to see objects which are in our galaxy, you should wait for way longer than the time span of a PhD. So betting your PhD work on that wouldn't be a safe choice. But they say, wait, if we can see many galaxies, if we can see 10 to the 5, 10 to the 6 galaxies, then we are guaranteed that we see at least one per year, okay? So how do we do to see 10 to the 6 galaxies? Well, to see 10 to the 6 galaxies, we must have a detector which is sensitive up to a volume where we do have 10 to the 6 galaxies, okay? And how much that should be? Well, we should look at least 100 megaparsec. No? If you look at 100 megaparsec, we multiply the density by the volume, and we get order of even more than 1 per year, okay? You see, depends on the volume, no? Depends on the cube. So it decreases very rapidly. So we really have to see up to at least 100 megaparsec, or farther away, of course. The farther, the better. But unless we are able to see things at 100 megaparsec, then we don't really see, the rate is just too small to see things on a human time scale, on 1 year, on 2 years, okay? So now we know that with LIGO data, they accumulated 2, 3 years of data, and we have 200 detection. So the rate nowadays is of the order of 1 per week, 1 or 2 per week. That's because we can really see much farther away than 100 megaparsec, and we can see binary black hole, heavy black holes, whereas this number that we have here was based on electromagnetic observation of binary neutron star. But this is still in the right ballpark of the order of 10 per million year, 10 coalescences per million year. But then again, we can expect to see one on a human time scale, I mean few in a human time scale, only if we are able to see at a megaparsec scale or beyond. The point is this detector able to see at the megaparsec scale or beyond? Yes. The answer is yes. Of course, now we know that yes, because otherwise. And then I want to tell you how this happens. I want to do the math of the reach of the detector and what is the typical intensity. And then I will wrap up this session about astrophenomenology. And in the last 10 minutes of today and the lecture of tomorrow, I will introduce you to how to compute the actual waveform in the post-Newtonian approximation. But this I will start at the end of today, I will do tomorrow. Now, in the next 10 minutes, I will wrap up this astro introduction. Any question about this big picture? Okay, I need to do some space here. Okay. So, to know how far can we see, we need two things. First, we need to know the sensitivity of the experiment, and second, we need to know the strength of the source. Okay. Of course, the two things go together. So what really matters is the ratio of the two. So let's start with the strength of the source. So for the strength of the source, well, where else to start than the Einstein equation? It's all in there, okay? So this equation is telling you how strong is the source. Well, we have to massage this a little bit. First thing that we do, we go to the linear limit. Let me be cavalier about factor. So this is a second order differential equation. At the end, you will have some wave equation for H bar. This will involve some gauge fix. I will do this later, but this is just for the order of magnitude, okay? There will be divergences of this, but basically the box of this wave will be sensitive to the energy momentum tensor. Again, dimensions are right. This is 1 over length square, and this is mass over volume, but G turns mass into a length, so this is 1 over length square. So what is the solution of this equation? Okay, I put the box down there, and I'm done. Okay, this is more than a joke, because this is just the green function of this. Again, I'm forgetting some factors here, no? But this is just the retarded green function of the box, okay? I'm just writing this as the convolution of 1 over r and the energy momentum tensor at retarded time. So let me skip all the details. Here we are interested just in the spatial components of the metric that are the ones responsible of stretching and squeezing the arms. We can derive this more thoroughly. Let's forget about the sorry, here I have just substituted. There's no more integration because I have just substituted the retarded time. No, this is h nu of tx. This is the observer, and this is the integral over the position of the source, and then the time of the observer is related to the time of the source by retarded time. So what I want to tell you is that this object is basically equal to the kinetic energy of my system divided by the distance of the observer to the source. Is it clear? I mean, so the typical amplitude of the gravitational wave is the kinetic energy divided by d, by the distance. Do you believe me? No, you shouldn't. I mean, this gravitational field contains many pieces, no? Contains radiative part and contains longitudinal part. Again, I don't have time to get into details of this. I will tell you more a bit later, but just to give you the order of magnitude. For instance, now you know that H00, if you solve for the Schwarzschild metric, you get a non-trivial H00, which is responsible for the Newtonian potential. Okay, that's physical, of course. The Newtonian potential is what keeps it here. But of course, this is not what we are looking at. We are not considering this part of the metric perturbation. We are considering only the radiative part. So the radiative part comes from the space component. Tomorrow I will derive more thoroughly. So the space component will have to do with the Tij. And then we have to integrate Tij over the source. Okay? So what I'm telling you now that the integration of Tij over the source is basically the kinetic energy of the source. And this is done via a trick which is a bit pedantic, so let me copy it to avoid the embarrassment of not getting to the right formula. What is that? Okay, here. So, what I want to use, I want to use a trick. Okay, this is the trick. So basically, I want to demonstrate this. That this object that comes here as the source, so of course, if you go a large distance, this becomes 1 over the distance, and doesn't depend on the position of the source, no? The position on this integral is over the source, which is kilometer, and this is megaparsec, which now I know it's 10 to the 19 kilometers, okay? So the x prime here, we forget it. The dependence of the size of the source here will be ultra important for the post-Newtonian approximation, but this I will tell you tomorrow. But for the time being, let's forget about retardation. Let's suppose there is a common retardation for all the points of the source. So this is just the integral over space of the energy momentum of the source over all the points of the source. So we have to do this, just this simple trick. Let's start with this. So Tij is inside the integral. Let's go here in some space. Tij inside the integral. Let's just write it as Tik xi comma k plus t, and then we have to symmetrize Tjk xi comma k, and then we put a 2. So this is a 3. I mean, let's forget the d3x. I'm just lazy to write the d3x. Okay, this is just trivial now because this gives me a delta jk, this gives me a delta ik, so this equation is trivial. Now I do some non-trivial thing. I trade this for integration by part, because I know that my source is confined here in this kilometer scale. So I move the integral on the other side, and then I get minus tik k xj minus tjk k xi. And now I use the conservation of the energy momentum tensor, and this is equal to ti0 dot xj, and this is tj0 dot xa. Okay? And then I do the same trick here, and I trade t0i xj plus t0j xi. I trade this for t0i t0k xi xj k. This is clear an identity, no? Because when I derive by k, I get this delta A. Yes, and then I do the integration by part. This is minus t0k k xi xj, and this is t00 xi xj. So here I got one derivatives, so I add one derivatives here. Okay? And so I related at the end of this computation Tij to the time derivative of the second moment of the monopole. The second moment of the mass is the quadrupole by definition. Okay? So modulo a factor of 2, this is the time derivative of the second moment of the mass, also known as the quadrupole, and so it's the second time derivative. This is exactly the kinetic energy I was looking for. Okay? So the magnitude of the gravitational wave is of the order of kinetic energy, so mv squared divided by distance. So we are talking about solar masses of the order of 10 kilometers times v squared divided by the distance, which for the megaparsec, let's put, we need to go to 100 megaparsec. 100 megaparsec is 100 times 3 times 10 to 19 kilometers. Okay? So this is just a back of the envelope computation to justify the fact that the amplitude of the gravitational wave is the kinetic energy. It's just double using of the conservation of the energy momentum tensor. You must have seen in standard GR courses. And the only thing I haven't justified is why I'm looking only to the Hij. Why am I not looking to the other components? Well, this is again due to the fact that the other components are responsible for other phenomenology of gravity, like the interaction between planets, the curvature, or the motion of the Earth around the Sun. It's like the photon, no? Photon and Coulomb attraction, they look very differently, but they all belong to the same electromagnetism. No? Electromagnetism is responsible for Coulomb attraction and repulsion and radiation. Phenomenologically, they look very differently, but they all both come from electromagnetism. And the same in gravity. You have standard attraction and repulsion. Sorry, you don't have repulsion in gravity. No, you have standard attraction, and you have the radiative effects. Here, by going to this part of the solution, we're just looking at the radiative part. Tomorrow I will justify this better, but this is just to get the order of magnitude. So if you think of a source of the order of 10 kilometer size in mass, and we put it at 100 megaparsec, yes. So here we get of the order 10 to the minus 21 v square. Okay, so this is the typical amplitude intensity that we should expect from the kind of sources we are looking at. So we need to go to the 100 megaparsec because otherwise the rate is too small. And if we need to go to the 10 solar masses, 50 solar masses, because that's the frequency we are looking at for our detector. And so we are stuck. The numerator is stuck, is fixed, the denominator is fixed. That's this number. So V is smaller than 1. So this is also a penalty price. But to say, oh, okay, but we are seeing things very close to merger, V is closer to 1. Still, we have 10 to the minus 21. There is not much escape. So we better build, or we better find the right experimentalist to build a detector that can reach this. And in practice, and this is luckily has been possible with present technology. I cancel this, okay? I erase. And this is really doable. If you just Google or open any paper about gravitational wave detection, you see this famous noise curve. So at 10 Hz, you have a steep rise in the noise curve. This is amplitude noise sensitivity as a function of frequency. Amplitude noise density, actually, is a function of frequency. So below the 10 Hz, you have the seismic wall. So basically, vibration of seismic doesn't mean earthquake, but there are seismic activities all the time. There is the sea wave hitting the seashore, even hundreds of kilometers away, propagating waves. And here you have short noise. Here you have all sorts of thermal noise. Okay, I don't want to enter in this detail also because I don't know much of them. But this is the typical figure that you see. So what is the scale that you see here? This is a logarithmic, log 10. And so basically, it almost gets to 10 to the minus 24. Okay? But then, if you look closely to this plot that you can find in any paper, there is the unit of this quantity, which is Hertz to the minus 1/2. Okay? So the noise, that's why it's called noise density. The noise that you see in all the papers about reporting about the noise level of LIGO, Virgo, Kagra, whatever experiment, is given in these units. So how do I compare with other thing that I just erased? There was mass divided by distance times v squared. This is dimensionless, of course. Mass is a length, and this is of the order 10 to minus 21. So this is the dimensionless strain that this detector is capable of measuring instantaneously. And this is the report that the experimentalist made for you. So you go to your favorite, I guess nobody's here an experimentalist, but you can ask your favorite experiment, oh, you have a detector, give me your spectral noise, your amplitude noise density, and we'll produce this plot or the equivalent of this for his own device, for his or her device. And they say, oh, cool, but wait. Okay, we need to compare this. How do we compare this? And I'll tell you, now, in the next 15 minutes, I will tell you how to compare this. So this is the theoretical prediction. I mean, for a 101 GR, this is good enough. And this is the thing we get from the experimentalist. How do we compare? Well, we compare in the following way. So here, let me erase this. So now we know, no? The galaxy collapse, and the two things match. H0 gives into account the critical density, which is more or less given by the local density of galaxies. And so this has to do with the noise. So first of all, why on Earth they give us these funny units? Why don't they give us the dimensional units? Well, the answer to this question is the following. So you have the output of the detector. So the output of this detector is just a time series. No? So you have the intensity of light. The intensity of light you relate it to the amplitude of the gravitational wave with this modulation. We already fixed the size of the experiment to have the maximum response to the size of modulation, and the intensity of light is proportional to 8. So let's assume that the output of the detector, we can reconstruct H, which is dimensionless, okay? So the output of the detector is H plus noise. This is dimensionless, this is dimensionless. So we want to go to Fourier space to characterize our noise. So we take basically, this is whenever you have to do with an experiment, you want the noise correlation function. That's the important thing to look at, okay? And then you basically, take the output of the detector for, say, 1 hour, you compute n tilde, and you compute n tilde another frequency, then you take another 1 hour, another 1 hour, another 1 hour, and then you average over the many chunks you collected. You can take 1 minute, 1 minute, 1 minute, or 1 day, 1 day, I mean, whatever. You just, today in the hands-on session, we can download some real LIGO data and do this computation. But, so what is the dimension of n tilde? This is time, right? This is dimensionless, so this is dimension of time. Okay, now, if you average on many, many events, what you would expect, no? This object is some amplitude that depends on the frequency times a phase that depends on the frequency. This other object is the same amplitude that depends on another frequency times a phase that depends on the other frequency. So when the frequencies are different, the noise has to be uncorrelated. So you would expect that the phases in one frequency and the phases in the other frequency are uncorrelated. So this object will involve the exponential of a random phase. So if you take this random phase for one, you add the random phase another, you expect that this is always 0, and is different from 0 only when f is equal to minus f prime, because this object is real, so its Fourier transform satisfies the reality condition that n of minus f is equal to n star of f. So when f happens to be to minus f prime, then the two phases cancel because they are mathematically one the opposite of the other. And so that's the only case where this average returns something non-zero. Again, this average doesn't return, if you just compute n and n tilde f prime for one realization, it doesn't give 0. It's only when you average of many chunks of data that it gives you a delta function of f plus f prime. Or if you want, you can do this, and then here you have minus f prime. It's proportional then to this delta function times some other function that is called the spectral noise density. And now the spectral noise density depends only on one frequency, because otherwise it's 0. So for some reason, there is a factor of 2 in the definition. Okay, so this is, if you like, it's a definition of the spectral noise density, but it's not only a definition because it includes some physical reasoning. The physical reasoning is that this average over many chunks gives you a delta. Okay, so it's half definition, half I'm plugging in some physical information. So it's not a trivial definition. So what happens here? This object has dimension of time, so this object has dimension of time. But this object is quadratic in the noise. So what is plotted here is the square root of that. And that's why it has dimension of inverse square root of hertz or square root of time, or square root of second, okay? Is it clear? This object is time squared, but it has a delta, and so the spectral noise density, which is quadratic in noise, has dimension of time. Then you may wonder, well, how weird, no? We have something that that is quadratic in the noise, but still depends only linear, as dimension is time. Well, if you play a little bit with the data, you should realize that this is the only meaningful quantity. This is the real figure of merit of whatever experiment you might be using. Why? Because suppose that you do this average over chunks of data of 1 hour, or you do this average over chunk of data of 2 hours, or 4 hours. Do you expect the amplitude of Fourier transform to be the same if you do the Fourier transform over 1 hour, 2 hours, 4 hours, given the same sample rate? No. If you do the Fourier transform over more data, the amplitude of the Fourier transform will be larger, of course. So the amplitude of the Fourier transform scales the square root of the number of data. Okay? So it doesn't make any sense that you provide the amplitude of the Fourier transform, because it depends on how long was your chunk of data. But that tells you nothing about the experiment. It tells you only about how lazy you have been in summing up data. Okay? So if you want a figure of merit which is really carry the information about the experiment, is not the Fourier transform, but it's the spectral noise density. You can check that this is insensitive to the size of the chunk of data you're using. That's because of this. When you go in real life, you do this over discrete sampling. No? You monitor the output of the detector some discrete times, so you get some discrete sampling. And so basically, this object is replaced by 1 over delta f, of course. No? The delta is the object that integrated over delta f gives 1. So in discrete sampling, this is replaced by 1 over delta f. And 1 over delta f is t, the total time you're using to compute the Fourier transform. So this tells you that the amplitude of the noise scale, the amplitude of the noise square, scale as the time you use to take the Fourier transform. You want to scale that out to obtain something that is independent on the specific way, on the specific data you use to compute the noise of your detector. So the spectral noise density is the physical thing to look at to characterize the figure of merit of the detector, but this is quadratic in the noise, so you may want to relate it to the square root of it, which is the amplitude noise density. Okay, so this is why you always see in the paper the amplitude noise density, which is units of square root of time, because it's the square root of this object. Okay, and now let's check how this has to be compared with the data. Okay, so we have an HFT that we very, very sketchily estimated here, and we have an HT of f, which is the Fourier transform of the H of t. Okay? Again, this is dimensionless, this is the dimension of time. Again, this doesn't directly relate to this, because this is the dimension of time, this is the dimension of square root of time. So we have to do some massage to compare the two. Let's do this massage now. Any questions so far while I clean the... Did you like my drawing? Shall I erase it? I feel sorry to erase it, but I need space. So, where is... Yeah. Did I lose my laptop? Yes. Question why I look for the right page of my notes? I'm finding... Okay, yes. So at the end of the day, I want to know how my signal relate to the noise of the detector. No? This is called signal-to-noise ratio. So we need to know how to characterize the noise of the detector, and we need to know what's the signal, the physical signal we want to compare to that. And when the signal is larger than the noise, then we are in good position to detect something. When the signal is smaller than the noise, usually we are not. Okay? So we want at least some rule of thumb to do this. So first thing, we need to have an estimation of the noise. So the idea is the following, that you will see later when I point you to the data, is that if you look instantaneously at the noise level, the instantaneous noise level is much larger than those 10 to the minus 21, the instantaneous noise. But that shouldn't worry you too much. That's what happens every day, you know, when you turn on the radio. So now there are radios, maybe people don't listen to radio anymore, they listen to the internet, but you know, in the old radio, you have a dial, okay? So the dial changes the frequency the radio is receiving at, no? Basically, there is, from the theory's point of view, very, very simplifying way to see it is a RC circuit. In RC circuit, you change the size of the condenser, so you change the response your circuit responds to. Okay, so the world is full of electromagnetic waves going around and making a lot of noise. So if you turn on your radio at random frequency, you just hear shh, just noise. But then if you tune to the right frequency, your radio station will step out of the noise. So what's the idea? That instantaneously, if you add up at one instant of time all the electromagnetic wave, it's a mess. But if you just filter out the right frequency bins, then you can see your, you can hear your signal loud, just because you're not taking all of the noise that appear at that instant of time, but you're just taking all of the noise that appear in that instant of time, but in a narrow frequency band. So the idea here is to reproduce the same, is that for the signal, we want to have something that is a correlation of the output of the detector with some filter, K, that we don't know yet. So this plays the role of the dial of the old radio. That's the filter. And the output of the detector will be signal plus noise. So what we want to do, or in Fourier transform, okay, we want to correlate in Fourier space the output of the detector with K, and in the correlation, I just forget the noise. I will say the noise will decorrelate from the filter. In the integral will fall out. So this is plus signal, but the noise will fall out in the correlation. And then I want to compare this with some noise. But then noise, by definition, has zero mean. So while it makes sense to talk about a mean signal, it doesn't make sense to talk about a zero noise. So the estimator for the noise will be this. We take the noise square and we average it, and then we expect to get something different from 0, and then we take the square root to put here in the denominator of the signal to noise ratio. Because if we just evaluate the average noise, that is supposed to be 0. Okay, so how do we do it? Well, the standard stuff. So we take the noise square. We just reproduce this formula, and then we take noise okay? This will be the noise square, our estimator for the variance of the noise. And then we substitute our formula. So first we go to Fourier space. This will be n of f, n of f prime. Sorry, let me use directly this formula here. It will be easier. Okay, so basically this is just the square of the standard, but for the noise we have to take the correlator to noise, because the average of 1 power of noise will be 0. And so okay, I'm just using the standard representation of the Fourier transform as the anti-Fourier transform. And so here what I get. Here I use the defining condition of the spectral noise density. At the end of the day, I get one integral alone. I get a 1/2 because of the convention, spectral noise density of my detector, and then I get k modulo square. So whatever is my filter, it will enter the definition, the estimation of the noise level in this way. Of course, the noise square will depend on the filter square and will depend linearly on the spectral noise density, because the spectral noise density is already quadratic in the noise. Okay, so at the end of the day, this shouldn't be a surprise. I mean, the only non-trivial ingredient that I added here is that the average of the noise is 0. So to have an estimator of the noise, we have to compute its variance. So okay, now we have a good estimate for the denominator, apart from the factor of, I mean, this is the square, so we have to put the square. A factor of 2 will be this. Okay, and then what is the numerator? Well, the numerator is this. Okay, so at the end of the day, you see, this object has all the right properties. It doesn't depend on the normalization of the filter. So if I scale the filter by any factor, that drops out. It only depends on the shape of the filter. It's linear in the signal and linear in the noise, because it's the square root. So this is just the right thing with, I mean, I didn't assume much. I just assumed that the mean value of the noise is 0. The only thing which is left is to find k. So what is the best k ever? The best k ever, the funny thing is that there is a unique solution to the best k ever. I mean, this might look a complicated problem, but there is a very elegant way to recast it in a very simple problem. Let's define a scalar product like this. Okay? All of this is a function of f, no? Minus infinity to infinity. I mean, this is a scalar product for L2 functions, no? I mean, it shouldn't be a problem. And now we rewrite the signal to noise ratio just in form of scalar products. We say that the signal to noise ratio will be equal to the scalar product of my signal to an unknown function divided by the norm of the unknown function. It is possible, yes. Just set u equal to 1/2 SNK. If U is equal to 1 SNK, then look at here. 1/2 or 2. You put SNK here, and this will give me KH, Sn simplified with Sn with the definition of the scalar product. And in the denominator, you get Sn multiplied by another Sn, give you the square, but then there is 1 over Sn that simplify. Sorry, you get SNK divided by Sn will give you SNK square, which is exactly what we had here in the denominator. Okay, so I have recast my signal to noise ratio into a ratio of 2 scalar products for this definition of scalar product. I mean, this is just a mathematical trick. This is my good estimator of a signal to noise ratio. I just throw out of the hat, this is just out of the hat, my definition of a scalar product. I mean, it's a good scalar product. I mean, it satisfies all the properties of the scalar product must have. And now, if this is my starting point, well, with this definition, my starting point becomes this. There might be factor of 2 coming. No, no, it's correct, because this will give me a 2, and this will give me 1 over square root of 2. So even the factor of 2 is correct. Okay, is everybody with me here? This is just the signal to noise ratio is the ratio of 2 scalar products. This ratio of the scalar product doesn't depend on the normalization of U. If I rescale U by constant, it doesn't change anything. But then what will be the optimal U to plug in to maximize the scalar product? My solution will be, can you see? This is a scalar product. U must be normalized to unity. So this, divided by this, just normalized to unity U. So U must be a vector normalized to unity that maximizes the scalar product with H. It must be H. I mean, normalized. Okay, so U must be H. That's the choice of U that maximizes the scalar product. But then U was this. That means that we have the solution for K. K is, apart from a factor of 2, is H divided by Sn. Okay? So let's plug in here. And then we get signal to noise ratio equal to, in the numerator, we have square root of 2 df H tilde K is equal to H tilde star times 2 Sn. And the numerator is U tilde, so is to the 1/2 integral in the f Sn and K modulo square. K modulo square will be 4 H modulo square divided by Sn square. See, the numerator and the denominator are basically the same. And so we get square root of 2 integral in the f H modulo square divided by Sn to the 1/2. Okay? So this is called my optimal matched filter. So K my choice of the filter, if I want to look for a signal H, is optimized by the choice. And as you can see, this makes a lot of sense, no? Because it means that if H contributes to some frequency, but the noise is very sensitive to this frequency, well, forget putting a filter that is sensitive to the frequency where Sn is large. No? Sn, you put it down here. So in the frequency where Sn is large, K should go to 0. Because it shouldn't allow to enter your analysis the frequency where a lot of noise is there. On the other hand, in the frequency where the spectrum of the noise is small, those are the ones where K should be large. Okay? So K is not enough K to follow H, but K has to follow the inverse of the noise. The only non-trivial information that we get here, I mean, at the end, the fact that the K must follow the signal and must follow the inverse of the noise, it was somehow, understandable. The only non-trivial information that K has to follow the inverse of the square of the noise. This is the spectral noise density, the square of the noise. Okay? This is slightly non-trivial. I mean, it could have been square root of Sn. It could be Sn to the square. I mean, this computation tells you exactly, okay? So at the end of the day, we get this. So another formula that you find often in literature is the signal-to-noise ratio square is equal to 4 integral from 0 to infinity h modulo square divided by n in the f. Why 4? Because I squared this becomes 2, but this was an integral from minus infinity to infinity, and this is an integral from 0 to infinity. So at the end, this is the standard formula that you get in literature. Okay, and it's over, but I have done. That's a long roundabout that tells you how to compare. So you take the amplitude noise density, and you compare to modulus of h, and you have done. Is this correct? So this is the spectral noise density, which is the square of the amplitude noise density. And you take the Fourier transform of your signal, you compare the two, and that's the right way to compare data to some prediction. No, you see? This is a df. This is dimensionless. This is df. This is time times times, because this is a Fourier transform of a dimensionless thing, so this has dimension times square. This is dimension of time. You cannot compare h squared to Sn, or you cannot compare h to square root of s. They have different units. So what you have to do this. So this is d log f. This is dimensionless. And now this has the same dimension of this, okay? So when you want to compare your prediction with the amplitude noise density, you better plot here, okay? These two quantities now have the same units and then can be compared. And you know that when they enter the signal-to-noise ratio in this simple way, just the ratio of the two, and you integrate over the logarithmic interval of frequency. Okay, and you know, just for the back of the envelope, the integrand is also the result of the integral when you're integrating over logarithmic scale. You know, if you integrate over the f, no, it matters. But if you're integrating over d log f, this is a small number after all. So basically, if you're able to estimate this, you're fine to know the signal-to-noise ratio. Okay? So just these are the tips that you need to know if you do your theoretical work and you do the hard work to compute the model, and then you want to compare to data, and you're stuck with different units, and you say, oh, how come? How do I compare? Okay, I think I gave you the map, no, to get an orientation how to compare your theory computation to the noise. So tomorrow I will do basically the prediction of this H tilde in the post-Newtonian. I will give you how to solve for the dynamics and how to use GR basically in a suitable approximation scheme, the post-Newtonian approximation scheme, to get this H tilde, and then I will pass the lecturer to more advanced stuff. This was introductory. You find in my notes, you find in many textbooks. Okay, I stop here.
Thanks, Riccardo, for the lecture. Are there any questions for Riccardo? Comments? Yes?
Okay, so now that you incorporated the signal-to-noise ratio into the plot, how do I read the plot? So I have to essentially have a much larger signal than that line.
Yeah, much larger. I mean, larger.
Yeah, okay.
Yes.
Yeah,
I
so
mean,
anything
this
in
of
the
course
middle
you
I
have to
don't
take
trust.
from the experimentalists. I mean, this you cannot predict.
Exactly.
You have to take the output of the experiment, do the Fourier transform, do the massage, and get this plot.
Okay, thank you.
But all these data are available. I mean, we can have an hands-on on this, how to download the data and do this plot. I mean, there are, as you can imagine, there are ultra-standard tools to do this.
Any other question or comment? Well, if you're not, let's thank Riccardo again. Go for the coffee break, which I think